although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper Rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyper Rulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Oh, I forgot the glasses. But full disclosure, this stream is brought to you by a MacBook Pro. We want to be open and transparent as much as we can. Ladies and gentlemen, Professor Stephen Wolfram.
Hello.
But this is fascinating, and just full disclosure, we were just talking very briefly before about certain things because especially when the pandemic hit, you decided to basically just kind of give back to the world, if you would, by hosting a whole bunch of live streams discussing science and technology. And that was kind of how I originally came across you and everything. And I was talking to my brother. He's like, no, Wolfram, the Mathematica thing. I had finished college right before, and the path I took didn't really expose it to me. And then I'm like, oh, is the guy that I saw on Professor Brian Keating with Dr. Eric Weinstein and everything. Then I saw you on Mr. Lex Friedman's podcast. I'm like, oh, this is fascinating. He's doing live streams to the world. I can actually ask questions and everything. And I reached out, and we are now here. So I think that's pretty cool.
Yeah, well, I have fun doing live streaming. I started because there was a pandemic, as we all know, and I figured there are all these kids who are not in school, and it's easy for me to provide sort of the backup science education thing, which maybe even would be more interesting than the not backup science education. Who's to know? But then I discovered it's a really interesting process, having questions from the world, including some from you, which I really appreciate, and being sort of forced to answer in real time on the spot. And there's just a ton of stuff in the last few years that I've figured out because I was on the spot having to answer a question, and I got to an answer which I wouldn't have gotten to otherwise. So it's been great for me.
It's definitely, it is a different characteristic. I had kind of gotten into the live streaming thing. I had kind of gone down more of the whole political route for a while. It kind of drained my soul, and science was my safe space. It was a place where I could go and just listen and just try to make connections, just try to see about what's actually going on. And like you were saying, just with these live streams here, I mean, I'm seeing different faces that I've noticed from some of your chats there. We got Kale, the progenitor of neutron decay cosmology. We have Rick, who knows something with the equivalence principle while working on a NASA problem. Apparently, that whole DART mission, you don't necessarily need to punch an asteroid to adjust its trajectory and stuff. Apparently, you could theoretically land on it, gather rocks, do the standard gravity tug thing, and then rather than continuing to waste fuel, just throw rocks. So I thought that was pretty cool.
That's cool.
We have Whitechapel here. We have WoW. We have Uncompetitive. TS. So that's the thing. You get to meet a whole bunch of different interesting folks and have questions where it may just seem like a simple question, but as you've shown actually, and it almost knocks me over, your big book here, NKS, from some very simple processes, you can get very complex behavior, and that didn't necessarily need to be the case.
Yep. It's lucky it is the case. Otherwise, we wouldn't have a meaningful universe.
I tend to agree with you on that. But let's just first off, for folks that may not know you, who is Stephen Wolfram?
Well, let's see. I remember many years ago, people ask me this. What do you do? Well, I do science. I run a tech company. I have been lucky enough to be able to sort of alternate between doing basic science and doing technology about 5 times so far in my life. And it's in terms of technology, the main thing I've built is things around what we call Wolfram language, which is a language that tries to represent sort of everything in the world computationally. So it's and that's led to Mathematica, which gets used by lots of people for doing technical kinds of computations, and Wolfram Alpha, which gets used by, well, lots of people doing lots of students, people in the world at large, there's a new user base for Wolfram Alpha that's about to be very big, which is AIs. And because they really need to ask questions to reading the internet and sort of putting together words based on what's on the internet isn't really the whole story. So the thing that's been really great about Wolfram Alpha is that we built this natural language interface to it as a way to be able to take sort of questions from humans and be able to put them in computational form and answer them. But now that interface is also a great interface for the current generation of AIs. So we'll see. It'll be interesting to see at what point the number of queries from AIs exceeds the number of queries from humans. That might be a sign of the coming AI civilization. Who's to know? But anyway, that's on the technology side. That's stuff that I do. Actually, was on the science side. Well, gosh, I started off when I was a kid, which was a depressingly long time ago, doing particle physics and cosmology, and then quickly discovered that I needed tools that were computational tools to do things I wanted to do in science. So started building technology. That's how I sort of got into that. But then got interested in this question of sort of how does complicated stuff happen in the world? And turned out that there wasn't really a good science answer to that. And so I sort of started trying to build kind of a paradigm for thinking about that. That led me to kind of questions about how do simple programs behave. Then this was early 1980s. I kind of discovered a bunch of things that were kind of shocking to me and very much violated my intuition about how things work. Basically that you can have, as you were alluding to, very simple programs can do very complicated things. We might have thought from our experience with engineering and so on, that if you want to make something complicated, you have to go lots of effort and set the thing up in a complicated way. But it turns out that's not true, that even really simple programs, when you run them, can do very complicated things. And that seems to be sort of the secret that nature uses to make lots of the complexity we see in nature. But that fact sort of turned into my efforts to kind of build a new kind of science that are based on simple programs rather than based on the sort of long tradition of mathematical equations that have kind of dominated the exact sciences for the last 300 or so years. So this is that kind of led me on a journey that started in the early 1980s and led through that big book you were just holding up, New Kind of Science, that came out in 2002, and led me back into technology and back into understanding what was possible in technology. And then, what was it, about I'm losing track of time, 3.5 years ago, led me back to a question that I'd long been interested in, which is sort of, how does the physical universe fundamentally work? What is the fundamental theory of physics? And I had ideas about that in the early 1990s, based on kind of this whole computational way of thinking about everything. But then, particularly thanks to a couple of young physicists who were like, you can't not do this. You got to, if this is going to work, you've got to push forward and do it. So I said, okay, if you help me do this, I'll try and do it. And so by the beginning of 2020, right when the pandemic started, actually, we had tremendous success in understanding sort of how fundamental physics is put together. And it's been really, really exciting because, you come up with kind of a theory in science, and usually you find, there's some data, and, some data agrees, some data disagrees. You have to kind of adapt your theory in this way or that way. Nothing like that has happened. We have a definite theory, and it's really hard to work out the consequences of that theory, but it's been a completely straight shot of, here's the theory. As soon as we work out a consequence, it turns out that consequence works out great. And it turns out that consequence is like what we actually see in the natural world and so on. And this has kept on going. And what's sort of even more surprising, in a sense, is that the kind of the paradigm that we've sort of been forced into by this thinking about fundamental physics turns out to be applicable to lots of other kinds of things as well. And so, for example, a big effort in mathematics and understanding the foundations of mathematics was sort of completed, what was it, at the beginning of this year, I guess. I'm losing track of time, terrible. Then And even like I've been working quite a lot on the current sort of round of AI innovations and so on. And she just wrote a piece that's turning into a little tiny book about how does ChatGPT, what is it doing and why does it work? Which I kind of more or less understand, and the answer is scientifically interesting. But one of the things that leads to is the whole question of, so what's going to happen with us and AIs, and are we in the last years of our species, so to speak, and is it all AIs all the way out, and so on? And I've been thinking about that. In fact, I've just been working on that last few days, and I've been going through these kind of waves of do I understand what's going on? Do I not understand what's going on? Is it all doom and gloom, or is there some opportunity for sort of us? And I've kind of come to realize that a core idea that comes out of basic science I've done, the idea of computational irreducibility, is probably what's going to kind of save us all. And it's kind of the same. It's the computational irreducibility is this idea that just because you know the program that something is running according to, just because you know the rules that something is operating according to, it doesn't mean you can immediately kind of jump ahead and say what the thing is going to do. There's this kind of irreducible computational process that's involved in working out what the consequences of some set of rules will be. And it's that, that irreducible computational process is what I think is kind of represents the passage of time in the universe for us, etc. But the fact that there's this kind of irreducibility, the fact you can't figure out what the outcome is without essentially following each step, just has tons and tons of consequences. And one of the consequences is, it's kind of, I was just thinking about it actually this morning, it's kind of the question, is there an apex intelligence, so to speak? We talk about in, trophic levels in ecology and so on, the apex predator. It's kind of like, is there a winning organism in some sense? Is there a winning sort of path to sort of where it's, this AI is the apex AI, so to speak? And what I realized is that computational irreducibility shows that will never be the case. That it's always just sort of for the same kinds of reasons that there's always more stuff to be invented. You never get to the point where all the things that you could, so in a sense, an invention, okay, when we think about sort of the passage of time in the universe and so on, there's this sort of irreducible computational process, and the in a sense, one of the things that is important to us is, at least in the current state of things, we live only finite lives. We have only a finite amount of time. So the question is, what can we achieve in that amount of time? And so anything that lets us kind of jump ahead, anything that lets us kind of beat a bit of computational irreducibility and sort of get more value from the time we have is a win. And so in a sense, the whole raft of automation, technology, even paradigms and ideas, they're all sort of stories of how do we jump ahead a bit? How do we, with automation, we, instead of, having to assemble all the pieces of your smartphone or something and then use it, things like that, you just have the smartphone. It's already assembled. You can yes, just like that, right? You can kind of you can leverage the fact that you've sort of already made this kind of computationally reducible jump to get something done. Same thing with ideas and paradigms and so on. You could say, well, there are all these particular detailed things one can say, but then one realizes there's some abstraction one can make that allows one to kind of jump over all those details and get to the result. I think it's so in a sense, the things that end up being of great value for us in technology, in the development of ideas, there are all these kinds of ways to jump ahead. And the question is, are there only a finite number of little jump ahead things to find, or is there an infinite collection of such things to find? And it's a sort of a theoretical consequence of computational irreducibility. There are always an infinite number of possible pockets of computational reducibility. There's never an end to inventions you can make. There's always another thing you can imagine doing where, some bizarre configuration of black holes that nobody ever thought about lets you do some weird hack in the universe or whatever else. You're never going to be able to say, we've invented everything that can be invented every sort of way of jumping ahead in the universe has already been found. And I think that's sort of part of what part of what one realizes is that that's sort of the reason that when we start thinking about kind of will the AI eventually take over, and it's just like, we're done now. This AI has figured out everything. There's nothing more to do. Okay, so there's another thing I figured out recently. So this is my last few days. But I've been curious. Okay, we all, people do jobs, they do different kinds of work and so on, and things evolve and there's more automation. And the question is, what happens to all these different kinds of work that people do? And, the pattern in history tends to be some technology enables some particular domain of work, like example, telephone switchboard operators enabled by the invention of telephones. Okay, so for a while, telephone switchboard operators are a thing, and there are more and more people who do that particular kind of thing. And then telephone switching gets automated, and nobody needs human telephone switchboard operators anymore. But what happens? Well, a lot more telephone switching happens. And then we build this whole stack of telecommunications technology on top of that possibility. If now there were human telephone switchboard operators, every one of us would have to be one of those in order to support the traffic that exists. But so what happened is, in a sense, there's this way of doing things that is done sort of by hand. There are lots of details about how it's done. Then there's kind of a level of automation, almost a level of abstraction that's generated that then sort of opens up another frontier of possibilities. And so I think the picture, and I was actually trying to verify this from actual data on jobs in the US for the last 150 years, but the data is rather messy and it's big pain to clean it up, which, I mean, our technology is the best there is for doing that, but it's still kind of a pain. But in any case, the thing that I'm sort of trying to understand is this process where you define a certain set of things that can be done, you automate those things, then the automation kind of opens a new frontier. And the thing to realize is that at that frontier, there are always many possibilities about where one can go. There's that opens up a lot of possible things. Like in current times, the LLM world has sort of opened up another set of possibilities for what AI can do and so on. And then the question is, well, which of those paths will actually be taken? And you kind of realize that this is a thing where there's no fundamental answer to this. There's no AI that's going to come in with some bag of mathematical axioms or something to say this is the right answer. This is something where there's sort of arbitrary choices to make, and those choices are that's the place where sort of, while we humans are in the loop, so to speak, that's the place where sort of we get to knit ourselves into this sort of computationally irreducible history of what happens. I mean, this is the thing that, again, if there wasn't computational irreducibility, the big AI could come in and just say, I figured it all out, history's over, the answer is 42 or whatever it might be. But this phenomenon of computational irreducibility just says that can't happen. It says there'll always be sort of a need for sort of, in a sense, creative decisions you can think of them of as for sort of which direction to go. So anyway, to me, it's interesting that these things that sort of come out of fundamental science end up, enmeshing themselves in sort of all these different questions about the world and sort of the human condition and so on. I mean, I suppose the other thing that's been a big thing for me very recently is this phenomenon of computational irreducibility. You can't know what's going to happen except by just doing the computations. That phenomenon on its own would sort of make our world completely unpredictable. If that was the only thing that was going on, we'd never be able to sort of say anything about what was happening in the world, because everything would be just like we would just have to wait and see what happens, just have to run the computation. But in fact, we as observers of the world end up being able to make all kinds of predictions. And the question is really sort of, how does that work? And the thing that I've kind of realized is there's this very interesting interplay between us as sort of limited observers of things and the underlying computational irreducibility of what's going on. That we are sort of computationally bounded observers of all of this complicated computation that's happening. We take certain slices through that complicated computation. There's an analogy which I happen to have explored quite a lot recently in just thinking about, I don't know, molecules bouncing around in a gas. We could be following every molecule, seeing what happens, working out all the details, but we don't. We just look at a large scale at, what's the overall pressure and temperature of the gas. Turns out if we looked at the individual molecules, it's all computationally irreducible. It's very hard to tell what will happen. But if we're looking just at pressure and temperature, turns out that there are simple gas laws. And so there's this sort of fundamental, there's this idea that when you're looking at things as a computationally bounded observer, you are sort of taking a slice that ends up showing computational reducibility, showing predictability, and so on. And the thing that I've kind of realized, which I'm all excited about, is that if you look at 20th century physics, there are three big theories of 20th century physics: general relativity, quantum mechanics, and statistical mechanics, the theory that leads to things like the second law of entropy increase, things like that. And what I realized recently is that all three of those theories are actually derivable from the interplay between computational irreducibility and our characteristics as observers. And so in a sense, what that also tells one is, if we were not as we are, if we were not computationally bounded observers who, for example, believe we're experiencing a sort of, we are persistent in time, if we did not have those characteristics, we would not observe physics as we observe it. But given that we have those characteristics, we inevitably have to observe physics as we observe it. And to me, it's very interesting to see how the laws of physics are emerging from characteristics of us as observers, so to speak. And it also kind of puts the pressure on trying to understand, well, what would physics be like if we were not as we are? So, I've long been interested in kind of, in a sense, different points of view. Some people, I'm always interested in different human points of view, but I'm also interested in more extreme different points of view of kind of, what do the dolphins think or whatever else. But it's really hard to sort of wrap one's brain around these sort of different, very different views of very different slices of sort of reality. And it's something that I think what really one realizes is that over the course of one's life, whatever else, one can sort of slowly move a little bit away from the way of thinking one had previously had. But this idea of sort of jumping to a completely different kind of thinking, it's really hard. I mean, it's something where in the history of our civilization, we make these little moves, we invent new paradigms, we go a certain distance. If you kind of, you can ask yourself, what would it be like to just be plopped into some completely different kind of domain of understanding? And we can have an idea of that, because when you look at simple programs, we can just pick a simple program at random and say, what does it do? Well, sometimes that simple program we'll look at it and we'll say, I recognize what that's doing. It's just making a fractal pattern or some such other thing. But sometimes it's just like, well, it's doing what it does. It's doing its kind of computationally irreducible thing. But I have no idea I have no way to take what it's doing and turn that into a kind of a human narrative, turn that into sort of form thoughts around what it's doing. And that's kind of what it feels like, I think, to be sort of put into this different domain, as I like to call it, Ruliad space, where you're kind of you're being sort of thrust into a different way of thinking about the universe, and it's tough, and we don't get to sort of, when we make a narrative about things, we're kind of there's certain things about which we get to make a narrative. There's certain things that are things we're used to, things that we, for example, have words for in languages and things like this. The question is, what is it like when you kind of jump out of that domain? I realize there's an experiment that I have to do, actually, which is, you look at an image generation, generative AI image generator, and, it makes something. Now, it's been trained based on images that us humans have made, that we put all over the web, the photographs we've taken of the natural world, things like this. The question is, if you change its mind, if you change its brain, you just start randomly poking at the insides of that neural net. What's it going to do? Well, it's going to do something. It's going to make pictures. But that thing you've got is now not, the thing that exists now is a mind that was essentially sort of forked off from the collective mind that we humans have and the natural world is presenting to us. It's a thing that is sort of our nature, so to speak. But if you start kind of messing around with its innards, it's going to be a mind that is not one that is sort of connected to us, doesn't have its sort of common history with us. And so I'm really curious what, I see your nice background there, and that's a thing that I can sort of more or less parse. What is that? I don't quite know what it is, but I can, I have some vague idea of what it is. Now the question is, as you start using a generative AI that is making something, but it's been distorted, it's been randomized relative to what we are used to. What will it make, and how will we be able to? Will it just look to us like it's just some random computational thing, and we don't have anything to say about it? We don't say it's a, I don't know what it is, a Firefox.
It's actually a blue eyes white dragon Ouroboros there. It's a
Oh.
cartoon character from what was a kid's show on anime while I was growing up. And this was actually the first piece of commissioned art I had done for myself by an artist. And basically it's the Ouroboros. It's basically the snake eating its tail. And then one of my other friends put the cool blue and orange fire background there and everything. So I think it's kind of cool.
But you see, you've got a story there. The Ouroboros is it's a name, it's a word, it's a cultural tradition. It's something that is sort of connected to our shared history, so to speak. If one was to define, the fractally eating snake that has, a fractal collection of tails, and it's gradually, eating a kind of transfinite number of tails in some weird way, that might be something that we have no, there's no sort of connection to what we, sort of the historical progression of things that we can even talk about. And I'd say it's a blah. And so what's a blah? Well, okay, there's this long story I have to tell you to explain what a blah is. Whereas as soon as you say Ouroboros, I have some idea of, what that is, because we have a certain shared sort of shared cultural history, so to speak. But I'm curious about, in a sense, a lot of what I've done in technology, for example, is trying to make sort of the computational language that represents the world as it exists, and sort of a way of sort of specifying that, so that both we can understand it with clarity and a computer can understand it with clarity. And that's kind of in a sense, the computational language is intended to capture those parts of what is computationally possible that we humans so far in our history care about. And I fully expect, and I've seen over the last 35 years that our computational language has existed. There's sort of been gradual expansion in the kinds of concepts that the language can talk about, because there's been an expansion in the kinds of concepts that sort of we in our sort of human culture and so on get to understand.
Well, I think this is fascinating. And one of the things I took away from some of your live streams back probably 2 or so years ago now was it was a live stream with Jonathan, and we were talking about the theorem solving ways, and we can come at it from the ground up or the top down. And it's like, well, I mean, that makes a lot of sense, but the maximum effective way to do that was not to just have the AI do it, was not to just have a human do it, but to have humans working with the AI in order to maximize results. And just in my opinion, that's going to be the way forward, being able to do that curation in order to search the computational universe for whatever we're looking for.
Yeah, I think that what we see in the current generation of AIs is something that is actually very similar to what we see being easily done by us humans. And that's probably not a coincidence, because the current generation of AIs are basically based on neural nets, and neural nets are a simple idealization of what we have available as hardware in our brains, so to speak. The hardware of actual neural nets hasn't quite reached some aspects of the hardware we have in our brains, and the hardware we have in our brains is kind of, really slow, for example, compared to the hardware we can make with electronics and so on. But it's sort of the same general architecture. And I mean, the history of neural nets is sort of a fascinating episode in the history of science, because neural nets are a very old idea. I mean, the basic concept of neural nets comes from 1943, and it if you look at what's inside ChatGPT today, it's really pretty much the same exact idea as was in the original McCulloch-Pitts neural net paper of 1943. It's much bigger. People were talking for a long time about, oh, what if I have a neural net with 5 neurons and so on. Now it's, what if I have a neural net with a few million neurons and a few billion weights, hundreds of billions of weights. But it's architecturally similar. And I think what one sees is that what we humans can do easily, whether it's generating, stringing together language, whether it's recognizing objects, those kinds of things, what we can do easily, now these neural nets can also begin to do easily. But there are other things in the computational universe. There are things which are computationally irreducible. There are things that require sort of many steps of computation. It's pretty hard for us to do that. I mean, we just about managed to do math. But if you feed us, you say, here's a program, run that in your head. Good luck. I don't know anybody who can do that.
I tried doing that as a kid and it always threw me off. I just get to, like, in my mind, an error 404. I'm like, why can't I figure this out? And I knew, I'm trying to figure out what billions of cells or trillions of cells are doing, which are each made up of molecules, which are each made up of atoms and quarks and everything like that. I'm like, okay, I think it's okay to not know all that stuff. And
right.
We have computers now, so it's cool.
Right. I mean, I think the thing is that there's this sort of, our brains and our neural nets aren't good at deep kind of computationally irreducible computation. It's not a it's a complicated thing to go through and sort of loop through all those different steps of computation. But it is something which electronics and many aspects of the natural world are really good at doing. And so now the question is sort of, what's the interface between kind of the stuff that neural nets are good at doing and our brains are good at doing quickly, and the stuff that is possible in the computational universe. And I think this is a place where I'm happy to say the thing I've spent decades on of building this computational language is really useful, because it is an interface between this sort of the structured computation that can be done and this kind of broad but not very deep sort of collection of experiences and data about the world, and sort of the cultural story of this is the trillion words of text that exist on the web, and now you can kind of recognize the patterns in that and make a sort of simple inference about what might come next or whatever else. So I think it's this idea of kind of use computational tools. We've used tools from the natural world for a long time, and those tools from the natural world, again, sometimes make use of what we can think of as deeper computation, more steps of more kind of computational steps. And that's, I agree that that's kind of the interesting way forward, the interesting way for us to kind of leverage what exists, what is computationally possible, even though we have this broad but rather shallow kind of computational ability of our own. I mean, but that broad but shallow computational ability, the fact that that's how we work, is why we perceive the physical world the way we perceive the physical world. And it's, I think, but as a practical matter, it's kind of like, well, okay, where do one of the things I've just been sort of thinking about, I've thought about it in the past, but I think my thinking sort of gradually evolves. Is kind of, okay, so where do we humans fit into this whole picture, and kind of what is it like when I mean, if we really skip to the sort of the end point, I mean, one of the things that we can see right now with automation is you define a goal, you as a human define a goal, then if you're lucky, there's an automated system that goes and sort of executes on that goal. But it's still the case that the humans have to invent the goals. And so now a question would be, well, you can start having AIs suggest, well, why don't you think about this goal? Why don't you think about that goal? And then you start thinking about, well, how do human goals evolve? How do we take this whole system of humans and AIs and so on, and how do we answer sort of what's going to happen in the future for what people or AIs, what the whole system is going to choose to do, so to speak. And so I've been curious, is it the case that in the end, it could be a very bad situation where in the end, sort of the evolution of all goals is to some kind of fixed point where nothing happens. It's just like, we're done. There's there's nothing further to do, so to speak. Again, computational irreducibility comes to the rescue. That will not happen. There will always be more things to do. There'll always be sort of more places to explore, so to speak. And I think that's when we look at kind of it's sort of a okay. So one of the questions is, can you stop? Could you stop progress? Could you just decide we've got enough? We're done. We don't need any more. We don't need any more inventions. We don't need any more sort of development. And what you realize is that again is not possible, because what happens is that this sort of computational irreducible process of what happens in the world will always throw up unexpected things. There'll always be, as if it didn't throw up unexpected things, you'd be able to say what its outcome is. So the very fact that it's computationally irreducible means that it will inevitably produce unexpected things. And as soon as it's producing unexpected things, that wonderful system you built that just finishes everything has a little hole punched in it because something unexpected happened that it wasn't set up for. And that's inevitably going to happen. So there isn't this way of sort of putting this sort of cap on everything and saying, we're done now. We don't have to worry about anything else. So I think that's, there's sort of this inevitable, unending progress in a sense that will happen. And, we've seen it in biological evolution. By the way, I realized one thing recently about biological evolution. One of the questions that always comes up is, biological evolution, one might say, can it get there from here? I think this came up on one of the live streams recently, actually. I think this is where I figured it out. It's this, people say, we've got, our eyes have, have the cross connections in front of the retina, which is really goofy, but squids have them behind the retina, which is a much better idea. But evolution can never get from here to there. We're stuck. Okay, that's the exact same thing people said about neural nets before 2012. People said, look, we try to learn the weights for a neural net so that it can reproduce these examples and so on, but we just can't get there from here because the thing gets stuck. It's like it's on a mountainscape and you're trying to find the minimum point. You're trying to find the lowest point on the mountain, and you keep on doing that by moving from every point to a lower point near you. And then, that doesn't work to get you to the minimum point because you get stuck in some mountain lake somewhere that was, is a local minimum, but not the global minimum. And so what people had always thought is, if it doesn't work on the simple cases, it doesn't have a hope in more complicated cases. Turns out, unexpectedly, to me at least, and I think to other people too, that intuition is wrong. In other words, it turns out this was the big surprise in neural nets and deep learning in 2012 was harder problems are actually easier. So in other words, you might have thought the toy problem with the simple configuration of this, that, and the other would be a thing you could reasonably do with a neural net, but then if it got more complicated, you wouldn't be able to do it anymore. That's what I thought. I worked on neural nets a bit at the beginning of the 1980s and played around with them and didn't manage to get them to do anything terribly interesting. And that's what I assumed was that to make them do something interesting, to make them do something sort of hard would be more difficult than making them do something sort of easier, simpler. But it isn't true. The reason it isn't true is when you are dealing with a neural net that has, a million, a billion weights, that many knobs to turn, it's like you're in this very high dimensional space and you don't get stuck anymore because there's always a way out. You think you're getting stuck in the mountain lake because you can only go left or right, or forwards or backwards. But actually, there's 100 billion different directions you can go in, and one of those directions is going to be a way out.
So more degrees of freedom per se.
Yes.
Cool.
And this was the thing. One, the idea that one could sort of reach the minimum, so to speak, by when one had enough degrees of freedom that one could sort of get out of locally being stuck, was something that didn't really occur. And I kind of suspect that evolution has the same trick going on. That in fact, when we think it's getting stuck, that it's and there are cases where we can see, evolution is very conservative. I mean, we have so many things in us humans. It's like you say, oh well, there's this feature of us humans, some aspect of some organ or some such other thing, and then you say, how long has it been that way? You realize it's been that way for 200 million years. We are the descendants of, that organ existed, maybe it's even 500 million years. Maybe that organ existed in the trilobites or whatever else. And it's been, just conservatively sort of reused over and over again in the history of biological evolution. But I kind of was, I've kind of had this assumption that evolution has this kind of fundamental characteristic of getting stuck. And I think one of the things that I realized is that intuition may not be right. And the fact that it isn't right is something that we sort of start to learn from what we've seen in neural nets and so on.
So that what you've just kind of been describing over the past few minutes, Professor, is the sheer fact that computational irreducibility is a thing. It just, for me as a lifelong gamer, it sounds like the game must be played to actually see what the outcomes are. And the fact that computational reducibility exists, just because yesterday was March 10th, aka Mario Day, because if you take MAR and then the 1 and 0, it kind of spells Mario, and they have the movie coming out and everything. But basically within Mario 3, there were these warp flutes that allowed you to literally warp ahead several zones. And by achieving that, in that case, a magical item, you were able to warp ahead. But it sounds like, and this is part of one of the reasons why I want to have you here on the live stream, is that with the physics projects, with being able to move ahead, if we can find some level of computational reducibility within physics, within technology, how may that let humanity warp ahead, so to speak?
Right. Well, good question. I think, we'll always find, there will always be pockets of reducibility to find. What will be the really exciting ones to find? That's a good question. I mean, in a sense, it is, inevitably going to be one of these computationally irreducible questions to know what pockets of reducibility there are out there to find. But if you ask, there are some things that seem pretty obvious as one thing that I think still needs a bit of unraveling, actually, in terms of ideas, is the following point. When we look at materials today, they are just, made of some collection of molecules. They just do what they do. If we go back even 100 years ago, there weren't artificial materials. There were only materials that somehow existed in the natural world and were made by there were not things that, you could refine them, but there weren't things that were sort of not of the natural world. Then things like plastic came along that were things where that just didn't exist in the natural world, but we could make it. But it's still just a material. It's just something, it holds things, it has some strength, et cetera, et cetera, et cetera. But it's not like it does a computation. And I think one of the things that sort of I've been, I wondered about is, in today's world, it's like we're used to the fact there are computers all over the place. In the future, people will be surprised that everything wasn't made of computers. That is, that anybody even ever considered, I'm just going to have a case for my phone. It's just going to be made of plastic. It doesn't do anything. It's not a computational, it's not sort of programmable, computational all the way down. Now, what's tricky about this, and I have to say, I'm not sure I've entirely untangled it all, is when you say everything is made of computers, what you're essentially saying is things are constructed, all matter is programmable, and all all things are capable of being of somehow being specified from the outside what they're going to do, and then they follow certain rules and do it. Now, of course, in nature and physics in general, that's what's already happening. Things are following certain rules. But what one's kind of saying is, oh, but one can have some way from the outside to change the rules. It's a little bit philosophically complicated, but I think as a practical matter, it's something where, it will be, as we untangle how that works, I think that will be one of the things that will get pretty interesting in terms of the future of technology. I think that right now, for example, we biological organisms are the only example of molecular scale computation that we know. But in a sense, in the future, one can imagine that there's sort of molecular scale computation everywhere in everything we deal with. And that both sort of breaks down the specialness of life as a user of molecular computation, and also gives us a lot of potential for sort of how we can essentially form the world in a way that we determine, rather than just the way that nature has delivered to us. I think that a basic example of that is in robotics, for example. There's one of the things I've long assumed will eventually happen is general purpose robotics, just as there's general purpose computing, that one will be able to have this pile of things, maybe they're even just molecules, that essentially reform themselves to achieve goals that we have. Now, what gets philosophically tricky there is to define what are those goals? What do we want it to do? We say, here's a pile of molecules, here's a pile of weird little objects that form themselves in some robotic way. Okay, what do we want it to do? We say, well, we want it just to form itself in some robotic way. Well, that's not good enough. We say, we want it to walk, let's say. Walk is a very high-level concept. There are many ways to walk, as maybe Monty Python demonstrated. But I think that the thing that is then sort of, how do we take a high-level description, a high-level sort of narrative description that we have, and how does that turn into something that actually gets executed, implemented? How does that work? Is it the case that when we have this different implementation layer, that we can have very different sort of things that we can imagine specifying at the sort of narrative level? The narrative level we have is based on sort of the evolution of our language, et cetera, et cetera, et cetera. But there are these sort of there's a whole kind of computational universe of possibilities that we're not yet tapping into. And these are sort of ways that we'll sort of have easier exposure to that. I think it's this question of what what is possible given this sort of computational paradigm. What do we start thinking about? What do we start sort of imagining? There are just all these different areas one could think about. One could think about, how does the world decide what to do? Because there are a bunch of things in the world that sort of have to be somewhat centrally decided. Like, for the time being, you say people have to drive on the left-hand side of the road or the right-hand side of the road. You can't not decide that. That has to be collectively decided. Of course, as you imagine the future, you might say, well, actually, at some point, you won't have to decide that, because at some point, all of these self-driving cars will all be able to figure that out, and it doesn't really matter. And they'll just, at every encounter, they'll just sort of work it out between themselves, and you won't have to have defined that collectively. But somehow it's still the case that we, in the world as it is today, it seems like, and I'm sort of trying to understand how this really works. It's kind of like the blockchain story. In order to, you've got all these transactions happening, but somehow you have to have consensus about what actually happened to put that block on the blockchain, to keep going, to sort of to build a solid past so that you can construct the future, so to speak. And the question is, kind of in a world full of humans and AIs, how does that really work? We've had certain systems in the world, whether it's democracy and things like this, which are based on the technology that we have, the entities that we have operating in the world. What are the possibilities? What can the possibilities be in the future? What do the possibilities have to be once we have kind of an AI civilization in parallel with our own sort of human civilization? How does that work? And so this is unsolved question. It's kind of like the you can do the exercise of thinking, what if you instead of having some you vote for this or that, you put check marks on a ballot or whatever else, you say, imagine that everybody writes a computational essay about what they want to be true in the world, and then all those computational essays are turned into a giant collection of feature vectors, and then they're all put together, and then some AI tries to optimize the world based on all of these feature vectors. It's a thought experiment. What happens in that case?
That sounds kind of like hyper legislation, in my opinion. What you were just talking about there, and just in my opinion, I believe the AI is just going to take after us, for better or worse. So I feel like if we put some more, personally, my opinion, I think most folks are good people. Just because you're a good person doesn't mean you don't do stupid S once in a while. I do it every single day. I started off when you popped in by exiting the browser and everything. So that's totally on me. We all make mistakes. How we handle them is what defines us. And just, I have to touch upon real quick, when you were talking about robotics and assemblies and everything, it almost sounds like you're talking about a form of computational alchemy, if you would, in the modern sense.
Yeah, it's a good term for it. Yeah. Yes, I think that's right. It's a nice term, actually. I mean, that term, it's the alchemists were concerned with, what can you make from, can you make, gold from lead and things like this. And this is kind of, can you make anything from that computational substrate? Yes, I think that is and that's, one thing we've already learnt. In computation, in our computers, we can pretty much make anything in our computers. And now the question is, can we translate that into making anything out of atoms and molecules and so on? And the answer, I'm sure, will be yes. Now, then the question is, will we discover we can do that right at the time when we decide, well, actually, our experience is better had in a purely virtual domain, so to speak. In other words, the implementing our experience with actual atoms and molecules and physicality is something that might not be the final story, so to speak. I mean, in the end, everything has a physical substrate, but the question is the stuff that we care about part of that physical substrate? And I think we already know that, minds are not the same as brains. A mind is something that has a more abstract concept than the physicality of a brain. And so, this question of sort of how do those peel apart is interesting. But I think for the time being, yes, I think it's a good term, computational alchemy, for what I think is possible to do, what one can expect to do in the world, and sort of to create whatever physical forms one wants.
Now, go on.
Yeah, please.
Oh, just in order to manipulate those underlying substrates, it kind of sounds like we're going to require some fundamental theory of physics. And if we can achieve that, then once we start to know more of what's actually going on within those underlying substrates, I mean, at that point, I think that solves a lot of problems within humanity that we have. If people didn't need to worry about where their next meal was coming from, and we could focus more on just actually interacting with other human beings, getting back I would love it to be back just like the mimetic of the past of Socrates is walking down the street and somebody would say, Socrates, well, what about this? And they would have some dialogue, and rather than just focusing on just like getting all the resources, trying to maximize our return on investment and everything like that. And I understand that's totally a thing. It's going to be like that for a while. But if we could actually focus on actually maybe exploring the cosmos, diversifying the planets on which humanity exists, just because I remember back in 2019, they gathered a whole bunch of really smart folks and had them run two extreme drills. One was a pandemic, one was a space rock. In those simulations, we failed both of them miserably. Now, it seems like real life kind of played out. We didn't handle one of those very well. The second one, I'd rather not get to that. I'd rather not have to deal with a space rock. I'd rather have us actually be able to focus on exploring the cosmos, because I think that would just be a new era for humanity. And get people excited, because humanity, we really need a win, I think. And hopefully the Wolfram Physics Project can kind of help us with this, just because it makes a lot of sense to me, in that I actually just started understanding yesterday in your live stream what the concept of Rulial space. I had heard it. I'd heard all these different things. I'm like, oh, it's just the perspective of there are these underlying rules and everything. And again, one of the things you noticed in NKS was that apparently within cellular automata, you only have primarily 4 real kind of almost categorizations of what's going on. And you think about all the potential rules you could have, but they tend to trend in those 4 particular ways for each unit of computation. It didn't need to be that way. So that's why when I saw you and then I saw Jonathan modeling like black hole merges and everything, I'm sitting there, I'm like, this young man is a wizard. He's literally doing computational wizardry, technomancy, if you would, in that you can actually start to visualize these in different ways. You have causal graphs, you have just all the different forms, and then you propose the whole concept of the Ruliad. I'm like, the professor is throwing down. He is literally just going to the point where, okay, I'm going to attempt to do everything, which kind of harkens back to one of perhaps your mentors, Professor Richard Feynman's concept of Feynman diagrams. We're just going to compute pretty much everything, see the most plausible routes, and see if we can figure out what's going on. And maybe you could kind of just touch upon quickly just the concept of hypergraphs and kind of how you've taken that step from cellular automata within NKS and applied it to the hypergraph realm.
Right. I mean, sort of the key idea there is, what is space made of? And it's sort of a funny thing that go back to the 1800s and people were still arguing, what's water made of? Is it just fundamentally continuous, or is it made of stuff? And it took until the early 1900s for people to realize, yes, water was made of discrete things, molecules. And then actually it was Einstein who first sort of said, well, what about the electromagnetic field? Maybe light and everything about electromagnetism is also made of discrete things, photons. But people never quite got the idea about space. Is space made of discrete stuff? And that's sort of the starting point for our physics project, is space is made of discrete stuff. Space is made of these things we call EAMs, atoms of space. And the sort of the only thing that one can say about these atoms of space is how they're related to each other. And the way to represent that is with a graph or a hypergraph that represents the relations between all these different atoms of space. And so just like in the case of something like water, got these molecules bouncing around underneath, each molecule just knows how to bounce off other molecules. But when you look at the aggregate behavior of those molecules, it follows the equations of fluid dynamics. Well, what happens when you look at the atoms of space and you see what they're sort of, as they evolve and change this hypergraph and so on, what is the aggregate behavior? It turns out the aggregate behavior seems to be Einstein's equations, the equations for the structure of space-time. And so Jonathan actually just recently, I think he just sent me this a few days ago, and I think it isn't finished yet, but it's his latest effort to really go from this hypergraph that represents the structure of space and see what that implies for the sort of large-scale structure of space-time and for things like black hole mergers and so on. And what's really kind of cool about that is what we really need to find. We need to find the Brownian motion of space. So in the history of studies of matter, people didn't know molecules existed. What was the evidence molecules existed? People said, well, it might be discrete. We don't know how big the molecules are, et cetera, et cetera, et cetera. But there was this phenomenon, Brownian motion. Put a little tiny pollen grain in some water, it gets kicked around. You can see that under a microscope. A guy called Robert Brown saw that in the 1830s under a microscope. Didn't know what caused it. Nobody knew what caused it until about 1900, when people realized actually it's molecules in the water kicking those pollen grains. And you're seeing the fact you see those individual discrete kicks is a sign that water is made of discrete stuff. So, the scales worked out so that you could actually observe that just looking through a regular light microscope and so on. You could observe kind of the atoms of matter, so to speak, the molecules of water or whatever else. So now our challenge is, can we observe the atoms of space? Can we find a phenomenon in the universe that is like Brownian motion was for material substances, that reveals the atoms of space. So normally when people try and simulate black holes, things like that, they start off from these continuous differential equations, things like that. They try to put them on a computer, they have to discretize them. If something about the discretization matters in the answer they give, they say, drat, there's something wrong with our numerical scheme. For us, because we're working sort of from underneath up, we start with this discrete structure of space-time. If there's something at the top that happens about these black holes or whatever else that is affected by that underlying structure, we say, fantastic, because we're then seeing, it's like a microscope letting us see down into the atoms of space. And so the things Jonathan is doing, for example, looking at actual sort of black hole mergers, things like this, actual structure of rotating black holes, things like this. As soon as if we can see things there that are kind of things that are affected by that underlying structure, then one has the potential to just go out. And my guess is, okay, that just like with Brownian motion have been known for basically 100 years, at the time when people realized this is a sign that matter is discrete. My guess is there's a phenomenon that's been known a long time, which once we untangle it, we'll say, oh my gosh, that should have shown us that space is discrete, should have shown us 50, 100 years ago that space is discrete, but we didn't know how to interpret that phenomenon, and now we do. And actually my best guess, my current best guess is dark matter is that phenomenon. It's been known for 100 years that galaxies, the rotation of galaxies, is not what you would expect based on the gravity of the luminous objects that we can see in galaxies. And the question is, what else is there? And it's, my current feeling is, if you look back at the history of studies of matter and so on, one of the big mysteries for a long time was, what is heat? Is heat some fluid, some substance that sort of suffuses matter? And that was the prevailing theory. The caloric theory of heat was the prevailing theory of heat. That's where our term calories comes from. But caloric meant the sort of the characteristics of heat that are not part of matter, that are just this thing that is heat, that isn't matter. And people didn't understand. It took until the 1800s, towards the end of the 1800s, before people understood that, in fact, heat wasn't a separate substance. Heat was a characteristic of motion of underlying molecules in an existing substance. And so similarly, my guess is that dark matter, people currently, they're off searching for particles of dark matter and things like this, because particles are what we know. Everything we know of is made of particles. But actually, it might not be that way. It might be that dark matter is a feature of the structure of space that isn't something that can readily be thought about in terms of particles, just like heat is not something that is readily thought about as a fluid. It's a different kind of thing. It's a different it's a different sort of instance of matter, not a different kind of matter, so to speak. So anyway, I'm kind of, one of the things that is sort of the big challenge, I would say right now, is one of the challenges with the physics project specifically is what are places, what are sort of actual things we can measure out in the world that show us that physics really works this way. I have no doubt this is how it will turn out. I mean, there's just way too much is fit together for this not to be basically what's going on. But the question is, can we, how do we kind of get our hands into what's actually going on? Now, once we do that, we may end up inventing technology. We may end up realizing, oh gosh, the way this works, the way this represents quantum mechanics means that if only we could build a system that had this kind of setup, then we will be able to do this thing that's super useful to us. By the way, I mean, this question of what's useful to us is not a trivial question. I mean, we could say there is this thing, it in principle works this way, that's all very nice, but we have no particular use for that. It's like, it's very nice that there's a phenomenon of, I don't know, superfluidity or something like this, but we don't know what it's good for. And I think that's always a challenge, is how do you connect? Well, let's take things like X-rays and gamma rays. You might say if we'd observed, we observed gamma rays, let's say, so what are these? What's this good for? Well, conveniently, this guy Röntgen in around 1900 realized that X-rays, which discovered at that time, were very good for like seeing through things, and that's a real good use case. Gamma rays, well, there are use cases, but they're not quite as obvious. But so, when we know things about fundamental physics, that we kind of have to go from two ends, so to speak. What do we know about the fundamental physics, and what do we care about doing? And can we meet in the middle and have something that is useful to us? And I think, one of the things that would be super useful to us is, for example, faster than light travel, or, some kind of, teleportation or some such other thing. And I did realize a while ago that our theory of physics implies that, in a sense, the problem of faster than light travel is, in some weird sense, just an engineering problem. It's you can think about it this way: when we have all the molecules in this room, bouncing around in the air, they're all hitting each other. They hit each other, a million times a second, whatever it is, and every time they hit, they're sort of thrown in a random direction. But if we could know if we could be riding on the molecules, and we could know at every collision, hey, I'm going to jump onto the other molecule because it's going to go in a better direction. And if we could always know that, we could probably get across the room at the speed of sound. Whereas the molecules normally will they'll hit one thing, they'll be thrown back that way, they'll slowly diffuse across the room. But if we could always pick which molecule to jump on, we'd be able to get across the room at, for example, in the case of at the speed of molecules, which is basically the speed of sound. Well, similarly, it turns out if in the structure of space, as space keeps reforming itself as it evolves, if we could somehow attach ourselves to that reforming structure of space, we could go, for example, faster than light in sort of relative to the overall structure of space. There's a bit of a problem, though. In order to be down at the level where two problems. First of all, we have to be capable of doing computations that are far beyond what we can actually achieve. This is a sort of biting in of computational irreducibility again. That's one thing. The other thing is we have to exist. We have to have our structure down at the level of atoms of space, which are incredibly tiny compared to us. And so if you say, can I send myself to such and such a place? Well, not unless you turn yourself into this sort of microscopic things that have a hard time even carrying enough information to send you, so to speak. So it's kind of a thing where, in principle, you could have something which, by doing enough computation, by being kind of small enough and so on, could be capable of going faster than light. But in practice, it's not possible. It's in practice for an entity like us, it's not possible to go faster than light. But it's not the case that, quotes, nothing can go faster than light. It is merely a feature of us as entities in the universe, as observers of the universe, that we can't do it. It's not the universe's fault, so to speak. It's just because of the nature that we have that we can't do it. But that's an example of a sort of extreme technological kind of thing where having said, well, it can't be done for entities like us, well, maybe there's some time technologically where it is useful to send an entity not like us. Like for example, one might have said, who needs, the only thing that's going to be useful is us traveling from here to there. So knowing that electromagnetic waves can send signals is irrelevant, because why do we care? We need to go from here to there. But actually, it turns out that our civilization and so on evolved to the point where you and I can be just communicating via...
This conversation wouldn't be happening right now.
Right. It's and it doesn't, our culture, our technology has evolved to the point where it's useful to us to have data be sent digitally rather than physically, so to speak. And I think it's rather than things being sent physically. And so, again, there's this kind of two-ended story of what's theoretically possible and what do we care about that have to merge together. And I think it's very interesting to think about. It's kind of an extreme exercise of imagination to say like, for example, take X-rays as an example. I don't think anybody thought about the possibility that there will be a thing like X-rays before there were X-rays. And it's like, what is, and for example, we now see with LLMs, for instance, the idea that you could have a thing that convincingly generates kind of human-like essays was not something that one immediately, one realized would be within reach. And it didn't look like it was within reach. Even last year, it didn't look like it was within reach. It's sort of a surprising threshold that got passed that is probably telling us deep things about the structure of human language and human thinking, but it's something that's now here, and now we can start seeing what its consequences are. But that, having the imagination of imagining a technology that, even imagining what we might want to do is not a trivial thing. And sometimes it's kind of, if we could imagine what we want to do, then we can think about how would we actually implement it. I mean, I suppose in my day job of running a tech company, in a sense, at least for the way that we tend to do things, a big part of the challenge is to imagine what's possible. I mean, when we started building Wolfram Alpha, for example, there was absolutely no reason to think that Wolfram Alpha would be possible. And well, I thought it would be possible. I had sort of science reasons and philosophy reasons for thinking it was possible, and said, let's try and build this thing. But even having this vision for what might be possible is critical in seeing what you can actually build. So I think that's the exercise, I suppose, for us now, is now that we can see more about the science from the physics project and so on, what might be imagined could be possible. What does it mean that there's if there's a maximum entanglement speed in quantum mechanics? What does that mean? Does that, we know about the speed of light and the consequences of the speed of light. We know about, things that are made possible by the way general relativity works and so on. It's still the case that the number of technological things that make use of special relativity is not that great. But it's, what things from the physics project can we use? And the main thing that we've seen is not so much physical things, but things that come out of the formalism from the physics project. That allows us to understand other kinds of things about distributed computing and other kinds of areas. And in a sense, the way the physics enters is as an analogy generator. That is, we're thinking, the same formalism applies to distributed computing, but now we already know that black holes work this or that way. We know that from physics. But because it's the same formalism, we can then go and import that formalism to distributed computing and make conclusions about it. And so, for example, one of the things that I'm interested in there is, just as we managed to kind of exist in the universe and kind of navigate, understand the universe, think about space-time, things like that, and we managed to sort of successfully operate in the universe, even though the universe is in parallel updating different parts of it. The universe is doing a giant example of distributed parallel computation. And so the question is, what can we learn from sort of our way of navigating the physical universe about doing arbitrary distributed computation? What can we learn about sort of from concepts from general relativity, things like this, about how we think about doing programming in parallel distributed computation? And I think there are going to be some big things there. I think that's I'm kind of looking forward to extending our computational language to this kind of multi-computational language idea, where there are many threads of history all operating at the same time, and trying to kind of understand what are the human accessible primitives that we perhaps know by analogy with our experience in physics that we can use to do this kind of multi-computational programming. That's one of the things. These are not easy problems. It's something, but that's one of the things I'm hoping to be able to pursue with that's sort of been opened up by the physics project. I mean, there's so many others. There's so many I mean, another one that I'd love to pursue is thinking about molecular biology and thinking about what are the important mechanisms really in molecular biology. One of the story from history is, go back in genetics before 1953, all a big mess, lots of different facts, no real overarching theory. Then it's, then DNA is the structure of DNA, the implications of DNA are discovered. And then, genetics started to make sense. So the question is, when we look at other areas of biology, what is the thing we need to make sense of what's happening at the scale of molecules in biology? And my guess is it's all to do with causal graphs and this kind of whole multi-computational idea. And traditional chemistry has kind of elided all of that away. It's roughly the issue is, in traditional chemistry, it's like every molecule, to know whether molecules are going to react, you just have to know how many molecules altogether are there. You don't need to know what was the specific molecule that underwent this reaction and that reaction and so on. It's kind of just like there are molecules are always meeting stranger molecules, so to speak, the molecules that are strangers to them, so to speak. It's kind of the same assumption as epidemiology models like SIR models. It's kind of like everybody is randomly meeting other people. They don't just hang out with their specific friends. Well, you know, for the same reasons those epidemiology models were totally wrong, the thing that which we already knew, by the way, within the first couple of weeks of the pandemic, you know, it was very clear that the actual detailed network of how people interact has huge effects on what actually will happen. But in any case, in chemistry, one sort of assumes this arbitrary mixing type phenomenon, and it's not really right. Molecules, you know, two molecules, they met before, they're going to meet again, and that whole causal graph of the successive interactions of molecules seems to matter, and that gives one a whole different view of what a sort of a whole different kind of chemistry, so to speak, which haven't worked out. But I'm guessing that that's important to how things actually work in molecular biology, and so that's another example. I noticed a comment there about computation everywhere, and I agree that this is the sort of the future of pretty much every kind of field of human endeavor. Call it X, is kind of computational X, and it's that's you know, in a sense, my sort of life work effort of building our computational language, it's all about being able to get to computational X in the easiest possible way, being able to think about things computationally, having a notation, a language to think about things computationally in. And it's kind of, you know, the idea, a lot of people say, well, you know, we can see computers are important, let's go study computer science. Computer science is great, but a lot of what computer science in practice means is doing low-level programming language programming. And it's kind of a phenomenon of, that's not what computational X is about. It's not about low-level programming. It's about understanding things computationally. And by the way, it's for somebody as ancient as me, you kind of, when I was getting into computers in the 1970s, you know, the first language I programmed in was assembly language. And people were still saying by the beginning of the 1980s, to do anything serious in computing, you got to be writing in assembly language. Well, people wouldn't say that anymore. There's a few levels of computation above that. But I think the thing that is being strikingly shown in the whole LLM story is that, you know, we're about to see, you know, in a sense, people are surprised. Oh, these LLMs can write lumps of code. Well, yes. That's, you know, if you look at, you know, computational language that I've been building for a long time, all of those repeated lumps of code, or we try to make it be the case that all those sufficiently repeated lumps of code are just built-in functions of the language. So in other words, rather than, oh, there's this big blob of Java code or something that represents, you know, this particular thing, it's just this one word in the language. Just like in human language, we have words for the things which we usefully want to talk about. And so kind of the idea is, you know, that's the path to automation. That's the computational reducibility jump, is we just turned that big lump of code into this sort of one word. And that's, you know, if there's a kind of a practical takeaway to these things that's very immediate, it's you know, this kind of computational language that we built, this is kind of the way to reach computational X for all X. And it's kind of a funny thing because, you know, I've watched the development of these things over the last 50 years or so, and it is shocking how slowly new ideas actually sort of take hold in the world. It's you know, there are things where, you know, I can kind of see, you know, you asked about sort of the future of inventions and things like this, you know, the kind of this idea of computational language, it's like, in 50, 100 years, it's like, oh, that was obvious. And today it's obvious to some set of people, but it's not as generally obvious. Likewise, an idea like computational irreducibility. Okay, I've been sort of living that idea for 40 something years now. One day that idea will be totally obvious to everybody. I mean, it's nice to see people like Jonathan, for example. For Jonathan, he's of a different generation, and for him, computational irreducibility is obvious. And it's important to see sort of when you've taken on board computational irreducibility as a paradigmatic idea, when you take on board computational language as a way of thinking about things, it's remarkable what sort of gets opened up and what becomes possible.
Well, that's the thing. It's like everything that we have now was built upon everything else that our ancestors built in the past now. And to harken back to a quote from Arthur C. Clarke, any sufficiently advanced technology is indistinguishable from magic. And I think a lot of what we're kind of seeing here, and again, just being a geeky, nerdy gamer myself, a lot of the things, it kind of reminds me of like a strategy game in which you'd start out, you have a small group of folks and everything. What are the basic things you need? Well, you need homes, so you need some housing, you need some farms to grow the food and everything. And very often these games are based upon conflict with other factions because we can do it computationally. We don't have to do it in real life. So then you would build up, you would grow your armies, but you would also research different technology. And as you unlock new levels of technology, that unlocks new particular units, new particular tools that one may have. And then by unlocking those new levels of tools and technology, you can continue to grow a larger and larger tower. But it's very important that you have a very solid foundation, because if not, you build that tower up and it's probably going to fall down. And to just give the folks a quick list of what goes through my mind when you talk about the Wolfram language and technology, and just go to Wolfram Alpha, just a website that's free. I type in speed, just gives us the physical quality, common symbols, length divided by time, meters per second. And the very interesting thing here, when we start talking about potential faster than speed of light travel, I noticed, and this was something that I don't hear many folks talk about, on Wolfram Alpha, the lower limit on the speed of quantum information is 1.6 times 10 to the 13 meters per second. The speed of light is approximately 2.998 times 10 to the 8 meters per second. And this has been on Wolfram Alpha for a while, and
that's interesting.
I think it's pretty neat. I think it's pretty well. Wasn't this proven recently with the entanglement experiment last year? Won I believe the Nobel Prize in Physics, showing that information per se is not necessarily localized. I mean, that's fascinating.
Right. That's cool. Actually, I should. You see, this is one of the things this is one of the facts about creating technology and so on, and particularly creating sort of open-ended technology. One has no idea what one's technology is going to do or be capable of, and I think it's a good example. Thank you.
No. Just the sheer fact that you're doing these things about ChatGPT, and just again, in my opinion, if we ever get to the point where we have the sentient AI and everything, again, I think it's going to take a look at humanity, and it's going to base itself on us, because we're going to be its learning model there. And I want to thank you for putting all those just good vibes, karma out there, if you would, because like you said, computers are our friends and everything. And if we treat them like friends, why wouldn't they be our friends back? And we could help build a better future there. And just the ability to utilize something like ChatGPT, to be able to give it the kernel of just knowledge base that is Wolfram Alpha. Basically, it's the computational knowledge engine that runs Siri and Alexa. And you have these very large companies out there that many of us use on a frequent and regular basis. And like, well, we could open up to the internet in general, or maybe we're going to trust Team Wolfram a little bit more. And I think that's something that's saying something just by people's actions.
Yeah, right. I mean, the thing is, what's there on the internet is static stuff. What we're trying to do in Wolfram Alpha and in Wolfram language is sort of arbitrarily deep computation. So, there's a thing where you can you pick the thing off the internet. But if you were talking about sort of the building of towers and so on, I think that's an interesting analogy. you're kind of if you want to actually do that non-trivial computation, you have to kind of build it on solid foundations. It's no good just saying, I mean, it's like, take a search engine, for example. You don't take the results of a search engine and build on them. You just take the results of a search engine and you as a human look at them and say, that's a good link, I'm going to go look at that. Because it's not been set up in such a way that it's sort of precisely defined what's coming out. It's just, well, these are convenient links. It's a different story to make this sort of solid computational structure that you can then keep building on. I think you have this whole question about, how do we tell the AIs what to do? How do we give them a model for how they should operate? And one of the challenges there is, you say, well, just show them what people do. Problem is, people actually think people don't do the right things. People say there's things that people actually do and there's things that people aspire to do. We really want the AIs to pay attention to the things that people aspire to do, but that's a much slipperier slope, because the things that the things we actually do, well, we actually do them. And there are examples of what we actually do. But most people would say, oh, but there are terrible things that we humans have done. Actually, what we want the AIs to do is the best that we humans could do. Let's pick out only the best stuff we humans do. And say, well, which stuff is the best stuff? Well, then you're in some horrible loop. And I think this is a it's a big challenge, and it's an interesting, I've as one of my kind of hobbies is doing stuff with kids and so on. And one of the things that I've always, since they get to be the generation that has to worry about these things, it's kind of like if you were writing the US Constitution today, and knowing everything you know about AIs and all this kind of thing, what would you actually say in it? What would it, what would be the rules that one aspires to follow, so to speak? And what would it's interesting, it's actually a very challenging problem. It's very unclear. And I think it needs real ideas about what, there are sort of, there's a structure that exists in, that, we found more or less kind of works, well, different in different countries, different things seem to more or less kind of work. And, the world hasn't blown itself up, at least yet, based on the things we're doing right now. But it's sort of a question of, given the capability of AIs and so on, what should we be doing? I think one of the things that is sort of a thing that sort of at least amuses me is the following observation. I mean, a lot of people's thinking about what we aspirationally should do, people look back to, whatever it was, things that were written down 2,000 years ago, or whatever else, as that's a good aspirational direction. It's good. That's but now when we think about the future, and we think about cases where there will be sort of, let's say, the computational alchemy, as you've called it, is possible. Many things are possible, and we have many more choices about what we could do, and many more constraints that exist in today's world. The sort of the scarcities of today's world won't exist. People will say, well, what should we do in this case? And I think one thing that may happen is people will say, let's look back to that time where we knew what people did and where we could see the live streams of the decisions people made and what actually happened when humans were still constrained humans, so to speak, before all these constraints got removed. Let's look back at those times to kind of get some sense of what it really means to be sort of a human going forward, so to speak. So I think, we may discover after the fact, when it's too late, that our times are more important to the future than we might think, because they may be the times that sort of define what, kind of what the human condition, when there still was a raw human condition to be exposed, so to speak, what we can get from looking at that. So I think, it's like to if some AI human thing is watching this very live stream at some point in the future, it's kind of like, yeah, right. It's Um, but
Well, I always like, sorry to cut you off, Professor,
Yeah.
but it's one of those things where I think about this and just in some of my greatest hopes, it's if we manage to not blow up the earth or something like that, and we manage to survive in 1,000 years, the internet archaeologists of the future looking back upon this live stream here, your live streams, and a lot of folks out there's live streams as well, just kind of seeing like, what were the ideas, how were humans struggling with these different things, how were they trying to come to some level of reconciliation, whether it's utilizing the blockchain, whether it's perhaps governance, whether perhaps it's trying to level up to computational alchemy. That's one of the things, and I just think it's fascinating because we all know rule 2 of the internet. The internet is forever.
That may be a good place to wrap up here.
I was gonna say we've been going on an hour and a half there. Thank you so much for your time, Professor, and everything. This is so fantastic. I'll make sure to I forgot to put the link to Wolfram Research in the channel right there. But just real quick, Tyler is he's commenting, computational irreducibility implies that AGI would need experience to achieve wisdom.
Good point. It's true.
It's kind of like intelligence is knowing a tomato is a fruit. Wisdom is knowing not to put a tomato in a fruit salad. But
very nice.
So thank you so much for everyone that's watching now and temporally in the future. And we have yet to prove that
the world exists on the top of a giant turtle.
Peace out, everybody.
Have you guys checked out the Memes of Destruction's channel? He's an interesting dude. I like